Lagrange's four-square theorem. Every positive integer can be written as the sum of four squares.
The theorem was posed and is also known as Bachet's conjecture. But the theorem remained unproved until Joseph Lagrange proved it in 1770.
Here are the examples of the four-squared theorem. 310 equals 17 squared plus 4 squared plus 2 squared plus 1 squared. These are more examples. Every natural number can be written as the sum of four squares, even if you have to square it to 0.
Here's our counterexample. 7 equals 2 squared plus 1. This is with 2 squares, and it obviously does not equal 7. Let's try 3 squares. 7 equals 2 squared plus 1 squared. This should be a 1 squared up here as well, plus 1 squared. And this does not give us 7 either. Let's try 4 squared. 7 equals 2 squared plus 1 squared plus 1 squared plus 1 squared. And now you can clearly see that this gives us 7.
To prove a theorem, we need to prove 3 lemmas. A lemma is a short theorem used in proving a larger theorem.
To prove Lagrange's four-square theorem, we have to prove lemma 1, which implies that the product of two numbers, each of which is a sum of 4 squares, is also a sum of 4 squares. Since every power of 2 is obviously either a square or a sum of 2 squares, it suffices to prove that every odd prime is a sum of 4 squares.
Lemma 2. If 2m is a sum of 2 squares, then so is m. Say 2m equals x squared plus y squared, then x and y are both even or odd, and this is the identity.
Many great mathematicians such as Fermat Euler, Carl Gustav, and Jacob Jacobi have used Lagrange's theorem as a building block for their own. This theorem is also important because now we know that any natural number can be expressed as a sum of 4 squares. Our conclusion: any natural number can be represented as the sum of 4 integer squares.